In the vast expanse of the cosmos, there lies a hidden language, a language written in the curves and contours of the universe itself. But to decipher this cosmic script, today we will embark on a journey. The universe secrets are written in the cryptic language of mathematics, and it is just not any other mathematics, but it is differential geometry. But hold on. How does it relate to general relativity? What is the connection between general relativity and curvature, and how does differential geometry tackle the intricate mathematics of this curvature? In this video, we will explore the intricate relationship between these two fields and explore and understand how they have shaped our understanding of the universe. This video is going to be very important for you in making you understand a bigger and a different perspective and picture of general relativity as well as differential geometry. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this lesson of differential geometry, where we are exploring and understanding the intricate link and the intricate details between differential geometry and general relativity. So before we go ahead and understand, we need to get an idea the objective of this video, because this video is going to be a little bit different with something very deep mathematical understanding. So the objective of this video is, number one, to establish and show you the link between general relativity and differential geometry, and this link is very crucial and important, and it is ignored in most of the studies. Also, I would like to show you the importance and significance of differential geometry, not only in terms of physics but in the entire arena of general relativity. I would also like to show you and establish that what is the learning path, what is the right approach which students should take in order to learn both general relativity and differential geometry, and what are the areas that you need to learn. Most importantly, I would also try to clear out certain misconceptions of general theory of relativity, because without a proper conception of differential geometry, learning or understanding general relativity is almost impossible. I will also try to provide an insight in the geometry of spacetime, because differential geometry is the only and the sole guide to learn properly the geometrical structure of spacetime, which actually is the pivotal idea behind differential general relativity. And overall, I will give you the suggestion of the correct book and what is basically the way in which to learn. So this is basically the objective of this video, but beyond that, there are certain things which I would like to also tell you coming up in the next part of this video. Now, if I take the general relativity and the differential geometry on both of the sides, then the first question which arises is that, shall I start with general relativity and then go to differential geometry? The question. Or shall I go from differential geometry starting with dg and then moving into gr? That is the question. So the question is that shall I learn the mathematics of general relativity or the differential geometry or the physics of general relativity? Shall I master the concepts of curved surfaces, or shall I first learn tensor calculus? What are the concepts that I would first learn? And most importantly, is general theory of relativity really a relativistic theory, or it is something else? Now these are the concepts, these are the questions that you might have, and this is the objective of this video, because this video is going to cover a lot of things. Apart from that, these questions will also be answered. So before I go ahead and start in the main part of the video, there is a quick and a small good news for you. That is, I am holding a webinar, absolutely free webinar on Einstein's General Theory of Relativity. Yes, for last 2 months it has been very successful and people around the globe have participated. It's an absolutely free webinar, and not only that, you are also eligible to get a participation certificate upon successful completion of the webinar. Now question is that how do you register? This is the time. It starts around 29th of October exactly at 8 p.m. Indian Standard Time. It will be held via Google Meet. So you are all welcome, whether you are from a science or a non-science background, doesn't matter. How do you register? It is quite simple. All you need to do is that you need to send an email to this ID, contact.physicsforstudents@gmail.com. Mention a little bit about your background, whether it is science or non-science, doesn't matter, and mention your WhatsApp number, because I would be sending you the Google Meet link on Sunday morning, that is the 29th, via your WhatsApp as well as through email. So this is a kind of a quick announcement. You can well enjoy the entire study and understanding of general theory of relativity on the 29th of October, and this is how we register. So having said that, the first thing which I would like to, I would say, understand or rather address is that what is differential geometry from a different perspective, not the usual definition. Now, if I take the two words differential first, which is the first, I would say, word, what does it mean is that it definitely includes differentiation, obviously. And the use of differentiation itself by default implies that it uses infinitesimal differences or differentials. That means the concept of calculus, and we can apply the rules of calculus. On the other hand, we have something which is called a geometry. Now, if we call it as a geometry, then obviously we are working with surfaces, structure, but the entire arena of physics, be it a kind of a Newtonian mechanics, general relativity, electrodynamics, anything which is happening usually takes place. Now, obviously, when I'm using calculus, particularly in this case, I would like to tell I am not using a flat space. So the underlying structure of the whole physics revolves around geometry. And that geometry is not something, a general geometry, it is using the rules of calculus. So together it makes up, I would say, differential and geometry. Now, so this is a kind of a quick definition that differential geometry is a branch that focuses primarily on the study of geometric properties, and obviously it uses calculus as a tool. Now, apart from that, it also uses derivatives. Why? Because differential geometry primarily deals with curves and surfaces and manifolds, and in a way that incorporates derivatives and calculus. It uses local analysis because differential geometry emphasizes the study of geometric properties at a local level, such as the behavior of curves and surfaces in the vicinity of a point. We also deal with tangent space, which is a key concept in differential geometry. In the notion of tangent spaces, we describe the local behavior of curves and surfaces and connections to differential equations, because many problems in differential geometry involve solving differential equations that describe how geometric objects change in response to the various factors. So overall, what we can tell from this part of the video is that differential geometry distinguishes itself from other branches of geometry by its heavy reliance on calculus and the consideration of local properties and changes in geometric objects. So I would say that this is basically in one shot, or I would say this is what differential geometry and differential geometry is all about. Now, still there is a question regarding the curvatures and what physicists tell. Let us look at a better demonstration this part of the video. So this is a kind of a very, I would say, a typical definition of differential geometry, uses the ideas and techniques of differential calculus. So if I get a kind of a curved surface, I am just mentioning this because a flat surface on which a curved surface is there, and this is the kind of a curved surface where the entire physics, whatever motion, force, electromagnetism, we have not defined what it is actually, is taking place. So the question is that, shall I go from the curved surface to the physics, or shall I go from the physics to the curved surface? Now, this is a kind of a I would say a philosophical understanding, or overall what it is all about. Where will we go from this part to this part, that we need to understand. So let us look on a very schematic diagram. So if I take this kind of a curved surface, then definitely we need to differentiate, and that is why the boxes are, because once we differentiate, and that is the reason we need calculus, and we will see soon that that is why gravity is caused due to local curvature. So if gravity is caused by local curvature, then how do we mention or measure this local curvature? Obviously by calculus. And that is why we study the local structure of space-time, and that is why differential geometry is called the study of the local surface. And we do not study global areas, and for that we need topology. So you can already understand that what is actually the distinction between differential geometry and topology. This is the first part deals particularly with the local nature, and the topology deals with the global structures. Because gravity, as we will see, is due to local curvature or local stress tensor which is caused, and that is why we use differential geometry in terms of measuring that. So you are already getting a kind of a hint that why and what is the relationship or the handshake between differential geometry and general relativity. But it is right now the time that we should look upon a different perspective, that what is general relativity, and then only we can get hold of this understanding. Now you see that around 1905 the special theory of relativity was published, and 10 years later the magnum opus 1915, the entire general theory of relativity, which refines the Newtonian mechanics into special theory, and it gave birth to general theory of relativity. So here is the Newtonian mechanics of objects from force 1 to force 2, which actually got generalized into curved space-time, which further got generalized into cosmology and study structure of black holes, white dwarfs, sun, etc. And straight lines, that was typically a notion of Euclidean space and Newtonian mechanics, now got generalized into geodesics. Time and space, which was quite different in Newtonian mechanics, got entangled into one single unit, which is called as space-time, and the Einstein's field equations, which deals with stress energy, etc. So we got the tensor components, not the force F equals to ma part of Newtonian mechanics. This gave rise to a number of implications like cosmology, black holes, gravitational time dilation, and gravitational waves. Now, after having said that, the most important thing which lies is this. So this is a kind of an equivalence principle demonstration, that the ball which is falling on an accelerating rocket behaves exactly the same way when it is identical with the ball falling on Earth. And this led to the conclusion of Einstein that gravity is not a force but a kind of a curvature. So this is basically the essence, the central idea of general theory of relativity, which we can summarize in this kind of an area. Gravity is not a force but rather a curvature of space-time. Space-time is a four-dimensional fabric including three spatial and one time dimension. Mass and energy causes the curvature. Objects follow curved geodesics, and more or less the general relativity is consistent with special relativity because it describes the behavior of objects which is moving close to the speed of light. Now, once we sum up the idea of general theory of relativity, there is something very striking which you could notice in this 1, 2, 3, 4 definitions. That is the notion of curvature, fabric, which is also a curvature, and curve and curve. So what we can understand is that now we are going deep into understanding the curvatures, because those definition actually portrays the idea of curvature. So now the concept is that curvature, if you are measuring, obviously we need differential geometry. So how curvature and differential geometry are intricately related to each other, let us look into the next part of our video. So as you see, we are dealing more with curvatures. And what is that? Let us look in the next part of our video. Curvatures and differential geometry. I would like to show you a kind of a diagram. Now you see, when we started with special theory of relativity, all we started are inertial frames of reference, speed and velocity, which is experimentally provable, and this is something which is called a frames of reference. But as soon as we move into general theory of relativity, what we find is we deal with non-inertial frames of reference. There is a gravity, geometry of space-time, which was not there in special theory, and it deals with a much more bigger and a larger scale. So these, I would say, are kind of a notion what general relativity and special theory of relativity deals with. So what we see is special theory is all about study of relativity, simultaneity, and obviously doesn't take gravity into account. General relativity is more about the study of geometry, and it leads to the surfaces and curvature. So what we see from here, that we will now going and delving deep into a subject which has got less of relativity, simultaneity, etc., and it involves more of geometry. Now, After having said that, if I mention some of the most important concepts or ideas of general theory of relativity, which are these: spacetime manifold, tensor, Ricci curvature, and those who already know differential geometry, you can see that most of these concepts are already covered in differential geometry. So all of this affine connection, parallel transport, even Einstein field equation actually shows this. All of them, all these concepts and ideas consist of geometry more rather than mathematics. Now hold on, it is not that I am not saying that mathematics is not there, but what I am trying to tell is that the geometry is more rather than purely relativity, simultaneity and mathematics. Now, having said that, let me give you a better idea by showing a kind of a schematic diagram. If I take general theory of relativity on the left hand side, and if I mention all those items of general theory of relativity, starting from gravitational time dilation to singularities, event horizons, you will see these are obviously very covariant in nature. I think I have explained in many of my videos what do I mean by covariant. It is basically a tensor term, and I've already started a video series on tensor which will be dealt with, and obviously it is non-linear in nature. Having said that, we get a much more clearer diagram that the relativistic effects of special relativity, whatever it has been, once it got generalized into the curved space-time, we got a huge paradigm shift. Not only that, we saw that there is a shift from relativity to geometry. We saw that there is a complete change in the mathematics, and our understanding of the coordinate systems totally changed, because it is less of the pure simultaneity and relativistic effects and more into geometry. Now, the whole idea why I'm showing is because the entire left hand side, all those outcomes of special theory of relativity, starting from Maxwell's equation, transformation, and when we go to the general theory of relativity, tensors, geodesics, etc., again you see that it tells that transition is from relativity to geometry. And not only that, the right hand side, all these are basically essential concepts of differential geometry and nothing more than that. So having established this fact that now we are going and delving into a subject of differential geometry which exclusively deals with curvature, and that is why the geometry. So now we have established the fact that we are dealing with a subject which is more geometric in nature rather than length contraction, time dilation, which consider the speed of light and the relativistic effects. Now it is the time that we should understand and know what is the relationship between differential geometry and general relativity, because we have established what is general relativity, we have established what is differential geometry. Now it is the time to see the relation between them. And before that, I would just like to show you that it is general theory of relativity is more about the relativity and simultaneity. So all these things on the left hand side box, these are nothing more than differential geometry, where we get a geometric understanding and understanding of curvatures, and it is more and more of intuitive in nature, and it includes exhaustive mathematics. So somebody, I think Neil Turok, has explained in one of his famous lectures that general relativity is more intuitive, where quantum mechanics is more mathematical. So let us move what I was talking about, what is the relationship between differential geometry and general relativity, and let us look into this part of the video. Now you see that when we talk about the relationship, we should understand that the entire general relativity is built on nothing but the mathematics of differential geometry. So if I take these curved surfaces, where the differential geometry usually deals, as we saw, with curved surfaces, and then we try to measure the dots, those points, those angles, those momentums, anything, and that is where general relativity actually starts with. So the curved surfaces or the geometry is the differential geometry part, and the physics which takes place is that of the general relativity. Now when we talk of physics, what are the important things which comes to our mind is that obviously the curved space-time, which is the main idea of general theory of relativity. Metric tensor, again, which is a very important, measures the causal structure of space-time. Einstein field equation, which is the groundbreaking work, and the main idea of general theory of relativity, which measures the space-time curvature and many other things, as well as the geodesic equation. So these are, I would say, concepts, ideas of differential geometry, full-fledgedly and completely depending on the physics framework of general theory of relativity. So what do we establish from this is this: the entire edifice of general relativity is built on nothing but differential geometry. Now when we talk about the entire edifice, then what are the concepts that general relativity has and which differential geometry is based on? The first thing is this one, which I have already showed you. You need to measure the curvature. That is why we need differential geometry. Straight lines are no more straight lines. These are geodesics. So you need the geodesic equation, again differential geometry. The manifolds that I have extensively dealt later in some of my videos of differential geometry, which we call the pseudo-Riemannian manifold. Again, it relies heavily on the mathematics of differential geometry. The other things like Ricci, curvature, tensor, etc., we will see more, also depends on differential geometry. And not only that, the extreme ideas and the extreme objects of cosmology like black holes and wormholes, the metrics, etc., all depends on nothing but the idea and the mathematics of differential geometry. So you see that we have explained that this is the relationship between differential geometry and general theory of relativity. Now obviously the question that comes to your mind, I can understand, is that what is the sequence of study? We understood the relation, this and this, differential geometry is the foundation of general relativity. But what is the sequence? I mean, how will you study? Let us look in the next part of our video. So if we take general relativity and differential geometry, the question is that do we go from general relativity to differential geometry or differential geometry to general relativity? Obviously, the answer is that we should go from differential geometry to general relativity. The reason is this one: the physics of relativity primarily centers on inertial frames and constant velocity motion, which was there in special theory of relativity. And the transition that we saw in general relativity focuses on space-time, which is a particular emphasis on the curvature. So what do we understand from here is that we should start at least with the basics of differential geometry and then go and understand the physics or the mathematics of general relativity. Now you see, when we talk of sequence, I also need to mention the concepts and how do we study. So first you start with curvature, understanding what is curvature and the entire mathematics. Then you go into what is manifold, very, very important, because the entire physics of general relativity is based on manifold. Then we go to tangent spaces, vector fields. Also learning geodesics is important. And sixth one would be Riemannian metric, and finally a little bit difficult and which takes time is called differential form. Now all those things, how will you study? What is the sequence? Why it is important? What are the books are being covered in my earlier videos? First, I would request you to look into this video, lesson number 20, where I have spoken extensively on the origin and the ideas and the concepts and the mathematics of learning manifold, which is very important for differential geometry as well as for GR. Also, I would request to look into this part of the video, which is called how to learn fundamental concept. What are the best books? What are the online resources? The sequence, the study, and a lot of detailed mathematical analysis and understanding how to learn fundamental concept, lesson number 19. These are the two videos which I feel if you look into this, it would be good. Apart from what are the books that you would study, I would say first start with curves and surfaces. Also understand Euclidean geometry, how it got generalized into non-Euclidean, and then these two very important books, Foundations of Euclidean Non-Euclidean Geometry and Worlds Out of Nothing, is a very interesting and a very good book on the history of differential geometry. And this is the video which I have made just a few days back, lesson number 21, which speaks about an entire, I would say, a kind of a review on the last book and how to learn and what is the importance, I would say, of the understanding the history of differential geometry and how these things actually happen. So you can go to lesson number 21. So all that we get from here is that these are the two areas, differential geometry and general relativity. So one is that there are different ways in which you can take up this subject. Number one is this one: you learn the differential geometry just as a subject. But because it deals with mathematics, pure mathematics, physics, engineering, computer science, I mean to say it has got a lot of reflections in terms of the real industry. Or you can do is that you learn differential geometry for learning general relativity. That means keeping in mind that I will learn GR, I'm learning differential geometry. And the third one is that you just learn those concepts of differential geometry which are actually relevant to general relativity. So now the question is that which approach or what you would take. That totally depends upon you. I leave the idea to you, but I have shown you what exactly and how things happen. Now, having said that, you might be thinking that, okay, this is so complex, these ideas are so very complex, but remember that you are not only the person who thinks differential geometry to be so complex. And one of the greatest genius on this earth, whom we consider Einstein, also find out a puzzle. So even Einstein faced the problem, and what is the problem is all about, we will explain in this part of the video, because this is something really very interesting and I think you should know. Now you see that it was Marcel Grossmann who was Einstein's classmate and a close friend at the Swiss Federal Institute of Technology in Zurich. And Grossmann was a talented mathematician, and I have spoken a lot about Grossmann in my earlier video on tensor part 1, and he played a crucial role in helping Einstein to learn about differential geometry. So here you see the three musketeers, Grossmann, Einstein and Bezout, and Grossmann introduced Einstein to the other works of differential geometry. So his role is actually indispensable, and you can understand that how Grossmann actually helped Einstein in understanding tensor calculus. So when Einstein left Prague around 1912, this is the Einstein house, and he actually met Grossmann, and the Grossmann family helped Einstein to migrate and settle up. So Grossmann during that time, was busy preparing the lecture which he was about to deliver at the International Congress. And after arriving at Zurich, you can see these two people become great friends. Indeed, great friends. And it was during this time that Grossmann actually started helping and developing the ideas of differential geometry, and I would say started teaching in some way to Einstein. And this is a kind of a line which Einstein spoke, that Grossmann, you have to help me, otherwise I will go crazy. So this is a kind of a famous letter which he wrote, and he told that, well, I am facing exclusively on the gravitational problem and believe that I can overcome all difficulties with the help of a mathematician friend of mine, and he's referring to Grossmann. Now the picture just below Einstein, I won't tell who the person is. I would wait for your comments if you can put this person right on the left hand side corner just below Einstein's photograph. Who is this person and who is he writing? Let me know in the comment box. This is a famous book of Abraham Pais, and where he actually shows Einstein's dilemma, that this problem remained insoluble, etc. And from him, that means Grossmann, he learned about Ricci and later about Riemann, etc. So you see that actually what happened from here is that this manuscript actually shows that Grossmann introduced Einstein the Riemannian tensor, which is important to general theory of relativity. And these are the writings which I have just elaborated using LaTeX code so that you can see it. And this is actually the insertion which called Grossmann's tensor for the fourth manifold. And this is how actually the entire fellowship and the friendship began, and this is how tensors got into Einstein's idea. So you see Marcel Grossmann and Albert Einstein, and Grossmann introduced Einstein to the work of Riemann, Levi-Civita and Gregorio Ricci Curbastro, who was developed the mathematical tools which was needed to describe the curvature of space-time, and Grossmann also helped Einstein to understand the physical implications of differential geometry. So I think that this actually shows the entire concept, and it was even Einstein who got perplexed, and it was Grossmann, a friend in need is a friend indeed, helped Einstein to overcome the ideas and get introduced into differential geometry. Now when we talk about Einstein, the first thing that it comes to our mind when we are talking about general theory of relativity is none other than Einstein's field equations. And how these Einstein field equations are related to differential geometry, let us look in the next part of the video. Einstein's field equation, first what I would do is that I will just tell you what are the constants, because you already know from maybe some of my videos on Einstein's field equation. This lambda is basically the capital lambda, the cosmological constant. This C4 is nothing more than what is called the speed of light, which was taken into account with the 4 dimensions. The 8 pi actually comes from the constant, and this comes from Poisson's equation. G is the good old Newton's gravitational constant, and these are actually the constants. But the constants are always constant. They really never bother our life. What bothers are the variables. And let us look into what are the variables of Einstein's field equation. First, I would start with R, which is called the Ricci curvature tensor. And it actually tells how the volume of matter changes when it moves from flat space to curved space. We move to the next R, which is called the Ricci scalar. And it keeps track of how the size of a ball deviates from Euclidean space. We also see what is called the G, which is the most important, and it is called the metric tensor, the centrifugal force, I would say, which revolves around Einstein's field equation. And there is something which is called Riemann curvature tensor, which is hidden because it's a contraction of Ricci tensor, which we will deal later part. And then we have T, which is called the stress energy momentum tensor. That means it keeps tracks of how things or matter moves around space-time. Now, I have explained in details about all those things which you can look into my other videos of Einstein's field equation. Now, what we see from here is that Einstein's field equations, which describes gravity and the curvature, are intrinsically or very intricately related to each other. What are the curvature and gravity? I would say this is an eternal connection. How they are related to each other, I would like to look into the next part of the video, where we are going to explore the important concepts of gravity and how it relates to the differential geometry's concept. So first thing is the metric tensor. Now don't worry, I won't be taking time to explain each and every components of that, which I have already done in my video in the playlist of General Theory of Relativity in my channel Physics for Students. You can look, but these are the basic ideas. It is a fundamental object. It captures the causal structure of space-time. You can say distance, volume, curvature, angle, and the gravitational potential. Everything is measured in terms of metric tensor. But still, because we deal with mathematics and we are students and learners of physics, this is not a complete idea. I will just give you a quick demonstration. Suppose I am located here and I'm going from this place to this place. I would take a route, which is this one. Now, this would say, I would say G, the metric tensor, as the distance, which I take on Euclidean path. Now, if I take a cab or a taxi and I get a pond, then I have to move around this path, and I would call this as a D taxi. So what I'm trying to tell is that metric tensor is nothing but a measurement. It is a measurement whether you're taking a straight path or a round path, whether you're going around the pond or you're skipping or jumping around. So this is just a metric, a measurement, a tool for measurement. Further, if I take, you can see that these are the lines or the contours on a space-time manifold, and this shows actually how close or dense they are compared to this, which are quite widespread. So these have got lots of gap and distance. So this one is much dense, this one is loose. And metric tensor in some way actually shows that whether we are standing on the loose surface or we are standing in a much denser surface. That means G depends on where actually I am. So I understand that this is not a very soothing and a clear idea in terms of mathematics, but you can look into my extensive video on metric tensor, which deals more with that, and I have calculated even the derivation of metric tensor. Now, apart from the curvature and gravity of metric tensor, most important is that this metric tensor and everything is taking place on a surface, right? So what is this surface about? This is what is called a manifold. So it comprises of two words, mani plus fold, and these are actually the origins from Northumbrian, West Saxon, etc., which I'm not going. The basic idea that we have to understand that when we are walking, talking, or doing whatever on a global surface, if we magnify that global surface, it should locally look Euclidean. So here are two definitions. This is a little bit technical. A manifold is a topological space that locally resembles Euclidean space. I would say in easy language, it is called manifold has a small area which looks like Euclidean. So the global structure where I'm walking or doing anything, it gets, I would say, magnified. It should look locally local. But why local? I mean to say, what is the advantage of making it looks like local? Let us look in the next part of our video. Now these are different manifolds. Okay, so this is called a positive curvature, this has got a zero curvature, this has got a negative curvature. Now most important is that all these yellow surfaces, they look locally Euclidean. That means if I zoom, all these will look locally Euclidean. What is the advantage? Simple, we can use the rules of calculus. So if I take a surface and if I differentiate it using calculus as dA, then when I magnify it, it will become this kind of a curvature from a manifold, and if I go furthermore into it, it will look like locally Euclidean. So what is the essence? What is the idea? The idea is this one. We apply the rules of calculus, and most importantly, this is what we are learning differential geometry. So one part we are done, as you can see that we talked about the metric tensor. It is a measurement. Now I am telling that the entire physics takes place on a surface which is called a manifold. This is already we have done. Now this manifold is actually measured by certain tensor components, which is again an integral part of differential geometry. Let us look into this part of the video. So first is what we call the Ricci curvature tensors, which actually measures how a shape is deformed. That means if I take a kind of a curved surface and I start walking from here, the line would go round about here and it would end somewhere here. And if I start walking from here also, my line would eventually go over here. So initial parallel lines which started began to deviate. And the presence of curvature, these geodesics start to deviate, and Ricci tensor, actually this r mu nu which we have just seen, is actually describing the volume change in each direction, how much the volume is changing. Now the question is that we have just seen lines. Where is the volume? We have not seen any volume. Let us look into the next part of our video. What do I mean by volume? So if I take a straight line and move the ball around straight over from here to here, we see there is no change in terms of volume. So the Ricci curvature is 0. Size of the ball remains the same. But if I take a kind of a path like this and I start moving the ball from here to here to here to here, what we see is the size of the ball shrinks. And if I take a weird surface like this and if I try to move the ball from here to here to here, it increases. So this actually shows the idea that how the size of the ball in terms of the I would say movement, it actually changes. So this is what is called curvature and gravity Ricci curvature tensor, which is another integral part of differential geometry. Now the second thing which actually rises is that what we call Riemann curvature tensor. And I would like to just show you a quick understanding what is Riemann curvature tensor. So I take a sphere, I am standing over here, and from this red dot I want to go to this blue dot. So I will keep the vector or a kind of a sphere or an arrow as straight as possible, and I move starting from the vector v, I move around here, here, here. And you see then again from this blue I want to move here. I'm trying to keep this straight, but the direction of the vector is changing because of the curvature. And then when finally I arrive over here, the v becomes v prime. That means there's a change in terms of the yellow vector and the final vector, which is this one, and that change is basically described by what is called a Riemann curvature tensor. So here is a Riemann curvature tensor, which is written in terms of Christoffel symbols, which is a technical thing I'm not going to tell in this video. And this actually denotes how much the vector has changed due to curvature from its original position, and it came back to the its change position. So if there's no change of vector, that means the parallel transport is something which is successful. But here we see a change. So the Riemann curvature tensor actually describes this, and it also describes the tidal forces in terms of general relativity. If you're really wondering what these tensors and you really want to know more, go back to my lesson number 21, which is called Einstein field equation for beginners. These things are dealt in much more details. These things are dealt with much more, I would say, mathematically, and you can look into that. Now, apart from the, when we talk of tensors and measurement of curvature, the extreme curvatures that we talk about comes from black holes. So you can see in this diagram, the neutron star has got a length which is more compared to that of the white dwarf, and even I would say black holes has got the extreme curvature. So here is the singularity and the length is more. That means the curvature, once we start understanding in terms of differential geometry, actually happens in case of black holes also. So in case of a flat surface, if I take a line which moves from here, in the curved surface, it will definitely take a turn around here. So what I'm trying to tell is that this sun, this neutron star, and this black hole, you can see the length of the black hole, the red one, is quite big. and it becomes infinite, it becomes extreme. So what do we understand right from here is that time is nothing but just an coordinate. So I start from here and take the time, the yellow one, to move over here. So obviously time takes more time to move compared to that of a flat space, and that is why we tell that time really slows down, and due to the extreme strong gravitational field which causes the curvature. Let me show you another interesting demonstration which will help you to understand. If I'm standing here and I move over here, then I take a kind of a simple Schwarzschild non-rotating black hole. So I start at 9 a.m. and when I move around black hole and I reach at the end, the time is 3 p.m. Comparing to that, if I take Earth, which has got a less curvature, obviously compared to that of a black hole, if I start at 9 a.m., then due to the less curvature, I reach there by 11 a.m. So here, what I'm trying to tell is that really time slows down, and this slowing down of the time is nothing but due to the extreme curvature. So these are the curvature and gravity. These are the components of differential geometry that we are dealing with. Now, time is just, remember, a coordinate in general relativity. Now, in this area, when we are closing down to a black hole or extreme gravitational forces, the most important thing that we are missing is that it is not a straight line. So if it is not a straight line, what it is? This is what is called a geodesic. So a straight line gets generalized into a curved space-time or a curvature. So the tram will move in the curved space, and the generalization actually gives rise to the curvature, and this curvature causes what is called gravity. So if the mass is causing a kind of a stress, then this stress is actually measured by stress energy momentum tensor. So the object moving through space-time is not only straight, but it is a geodesic, and this line will follow the curvature, and the curvature is because of the presence of mass, and mass is measured by stress energy tensor, and the curvature are defined by all those things which we are just speaking about: Riemann, Ricci curvature tensor, the metric tensor, and things like that. So this effect is what we call as gravity. So you understand now why it is important to understand differential geometry. The bending of the starlight also accounts for differential geometry, because if I move shine a light ray in absence of a mass, it would go straight. But if I put up a sun which has got a considerable amount of mass, it will cause a curvature, a dent in the fabric of space-time. If I shine the light from here, it won't go straight, but it will take the bent curved space-time. So the photon takes the path which is called the geodesic, and the curvature is because due to the presence of matter, and it actually proved in 1919 through Eddington's experiment that gravity is the bending of space due to matter. Now that we have dealt with black holes, etc., you might have a question that do we really need to learn differential geometry in order to study black holes? Because in black holes we have got a lot of other mathematics. But the question is that do you need to learn differential geometry to study black holes or any other kinds of mathematics? Let us look in the next part of our video. Obviously the answer is yes. The question is that why do we need to learn differential geometry, even to study cosmology and black holes? The first is the curved space-time, because black holes are basically intense gravitational fields. It warps the geometry, and differential geometry is the only tool which will help us to understand the curvature. The second is the event horizon, because differential geometry will help us to define the event horizon. It will help us to know the direct result of Schwarzschild radius and other things. The third thing is that we know that when objects are moving into the vicinity of black holes, they would not be straight, but they would be rather geodesics. So if it is a geodesic, then it is the only geodesic equation, which is a powerful tool of differential geometry. It will help us to understand and know more. Apart from that, what is also important is this one, Einstein's field equation, because the entire warping around the space-time, curvature, tensors, etc. deals with Einstein's field equation. And differential geometry is the only and one of the most powerful tool, because without that you won't be able to understand Einstein's field equation. gravitational lensing, which we have recently saw with the JWST telescope. So differential geometry exactly helps us to identify the angles and things like that, and characterizing singularities, because differential geometry helps to describe these singularities, the characteristics, the dynamics of the black hole, and to some extent also the thermodynamics of black holes. So I would say, having established that, what we are also looking is that these are the different metrics: the Schwarzschild metric, which considers non-rotating spherical black holes; the Kerr-Newman metric, which considers rotating and uncharged black holes; the Reisner-Nordstrom metric, which is, I would say, spherically symmetric black hole with an electric charge, but it has got no rotation; and the Kerr-de Sitter metric, which has got a cosmological constant; and Einstein-Rosen bridge, which is not a black hole, I would say, but it is called a wormhole metric. So all these metrics are actually depending on differential geometry, nothing more than that. So here on the right hand side bottom, you see differential geometry is used in many other aspects of the study, because the black hole thermodynamics, which I was just speaking about, provides us the mathematical language that we need to describe the curvature of space-time around black holes, and it helps us to understand the various geometric properties. So this is why you need differential geometry, the most indispensable and one of the most, I would say, a kind of a mandatory thing you can tell in learning general relativity. And this video actually shows and establishes the fact with different illustrations and mathematics that we need to know differential geometry, otherwise there is no way that we can understand mathematics of general relativity. So here is a time that we should quickly summarize on what we have learned today. So we have learned a lot of topics: differential geometry, how it relates. We also learned the study of differential geometry and its relation to curvature, how curvature and what are the concepts that differential geometry deals with, the relationship, how to study, most importantly, the books, what is a sequence. Even Einstein faced the problem, Ricci curvature, Riemann metric, and geodesics, and a lot of stuffs like that. And why it is important, you might have a question that I should study differential geometry, why it is required to know black holes, because it falls under cosmology. So I've showed you the answer. And the black hole metrics also depends wholeheartedly on the differential geometry. So we learned a lot of topics, but basically the idea was to establish and show you how and why differential geometry is so important in terms of general theory of relativity. So thank you very much for watching this video on my channel. If you have liked the video, please hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can contact me also in this email ID. This is my other channel on general theory of relativity, and you can follow me on my Facebook, LinkedIn, Instagram, and Twitter account. So don't miss for the upcoming videos, because a lot of events and other webinars which are coming up. Dr. Patel would be live on 22nd of October speaking about nuclear physics, etc. So Physics of Students will keep on surprising and providing good quality element of physics. And I will see you in the next video. But till then, goodbye.